The purpose of our research is to investigate how RLC circuits have applications in the real world. One way we discovered this happening was through radios. In this video, we will explain key concepts of how radios work and the physics behind it.
First, we wanted to start with an overview of RLC circuits. So as we already know, RLC circuits are comprised of a resistor, an inductor, and a capacitor, RLC, and an AC driving current or voltage across the entire system. So there are several key factors to consider in an RLC circuit for radio signaling. First and foremost is resonance. Resonance occurs at a specific frequency, F0. The angular frequency is mathematically easiest to use, so most of the time we use omega naught equals 2 pi F0 in order to define a resonant angular frequency. Impedance in a resonant RLC circuit is equal to just the resistance. And then the angular frequency can also be calculated by taking 1 over the square root of the inductance times the capacitance. This application is very similar to the weight on the spring model we learned in Physics 270, but an electrical instead of mechanical application. Resistance is often called undamped natural frequency and is given by omega naught equals 1 over the square root of L times C. It's the same value for a simple LC circuit, but in RLC circuits, peak resonance F0 depends on the value of the resistor and is called damped resonant frequency. There can be critical dampening, underdamp, and overdamp. As previously stated, damping is caused by R in the circuit, and it determines whether or not natural resonance will occur without a driving force. The damping factor zeta is useful when talking about damping and is dependent on the attenuation factor and omega naught. Bandwidth is a resonant effect that can be used to filter rapid changes in impedance near resonance. It can be used to pass or block signals close to the resonant frequency. It's measured between a cutoff frequency, the frequency at which power passed through the circuit has fallen to 1/2 of the value past at resonance. It's mathematically given by delta omega equals omega 2 minus omega 1, where omega 2 is the upper half of the power frequency, and omega 1 is the lower half of the power frequency. It can also be written as delta omega equals 2 times alpha, which relates it to attenuation and thus the factor zeta we discussed. A more practical measure of bandwidth is the fractional bandwidth, BF, which is equal to delta omega over delta naught, or omega naught, and it's often reported as a percentage. The Q factor is used to characterize resonators. Peak energy is stored in a circuit divided by the average energy dissipated in it per radian at resonance. Also be related to fractional bandwidth, where Q is a wide band and a high Q is a narrow band. Q is equal to 1 over the fractional bandwidth, which is just omega naught over delta omega. Q is directly proportional to selectivity, or how well a radio responds to the radio signal it's tuned to. For a series RL circuit, Q can be derived as to equal 1 over R times the square root of L over C. Derive the voltage across the resistor to be R times the current as a function of time, the voltage across the inductor to be L times the derivative of the current as a function of time, and then the voltage across the capacitor, which is the voltage at native state, plus 1 over the capacitance times the integral from 0 to the amount of time, and I as a function of tau, which is the time-related constant. To make a second order differential equation from this, you can derive two key things, 2 alpha and omega squared. Zeta is equal to alpha over omega naught, which is R over 2 times the square root of C over L. Based on the zeta, we get different transient responses where our differential equation can help us with really complicated derivations of current and decay frequency as a function of zeta.
So antennas are related to radios because they're how bandwidth is received and given. Antennas in terms of radios can be pictured as in a larger antenna receiving is the source and the receiving antenna is a radio such as in a car. Waves arrive and the receiver picks up this specific wavelength and frequency of a specific station. So you can position the antenna in a certain way to pick up different frequencies, and that will change your station. Antennas transmit and receive in the same manner, such as vertically polarized antennas will only transmit and receive from also vertically polarized fields. When the wavelength is transmitted and received by the antenna, it is able to feed energy onto it and be transmitted. Length is super important for this, for receiving signal. So that's why the length of the antenna, the longer it is, the more signal it can receive. But also capacitors and inductors may be used to make up for the short antenna to be able to fake a shorter and longer antenna and achieve resonance.
When you turn your radio tuner to a specific frequency, basically what your radio is going to do is it's going to look for that specific signal from the antenna, and then it's going to convert that to an intermediate frequency. You set it to 1200 kilohertz. Then you're going to actually take, let's say the bandwidth resonance frequency is 455 kilohertz. That's the frequency you want to achieve. So your radio, there's a little thing called an oscillator that's going to send out a frequency of 745 kilohertz. And so 1200 minus 745 kilohertz is 455 kilohertz. And that is the resonance frequency. So once you filter that resonance frequency through the bandwidth filter, then it's gonna hit a demodulator, and we'll explain that in depth a little bit later. And then it's gonna go through an amplifier, and eventually you'll hear it through the speakers on your radio. So next up, we're going to talk about low pass and high pass filters and how they come together to create a bandwidth filter. So here's a circuit for a low pass or a high pass filter. And to find the resonance frequency, the formula is
negative R resistor over 2 times the inductor plus the square root of the resistor over 2 times the inductor squared plus 1 over the resistor times the capacitor. So that's going to give your resonance.
all right. So a low pass filter is going to let through any frequencies that are lower than your resonance frequency. So here's the graph for the low pass filter, and the high pass filter is going to let all the frequencies through that are above your resonance frequency. When you have a low pass filter and a high pass filter together, you're actually going to create a band pass filter, and with this region right here being the bandwidth, and the frequencies that are above and below can't get through. So that's what the band pass filter is going to look like.
We've learned that bandpass filters are filters that pass signals within a certain band or spread of frequencies without destroying the input signal or introducing extra noise. Band of passing frequencies is known as bandwidth and is denoted BW. Bandwidth, the formula for it is the higher cutoff frequency minus the lower cutoff frequency, because bandwidth is defined as the frequency range that exists between two specified frequency cutoff points. Only a limited bandwidth over which an antenna design can operate efficiently. Over very wide, the antenna is known as log periodic antennas. Over very narrow bandwidths, the antenna is known as a resonant antenna. So the efficiency of bandwidth can be tested with a bandwidth test, denoting a theoretical figure for the data. Bandwidth in the radio is often 128 kilobytes per sec, and this is the unit that is denoted in a bandwidth test. Applications of bandwidth are included in computer networks. Demodulator is a circuit that is used in amplitude modulation and frequency modulation, so that it can separate information that was modulated onto the carrier from the carrier itself. Demodulator is the analog part of the modulator, and the modulator puts the information into a carrier wave at the transmitter, and then the demodulator pulls it so that it can be processed and used on the receiver end and heard by us through speakers from the radio.
In conclusion, we use the complex example of RLC circuits and how they relate to radio signaling to show the entire process from receiving a signal at the antenna to demodulation and then amplification through a speaker so we can hear what's being sent over radio waves.